Greetings, this is Artie from Artifact Electronics. In this episode we'll be looking at a Heathkit O-12 oscilloscope. This one was sold in 1957, and I think it was sold for about a year, after which its successor came out. It only came in kit form, but Heathkit was pretty famous for selling great kits, because the kits were complete, everything was included, except you had to supply your own tools and some solder maybe. They had great building instructions, step-by-step building instructions and pictures in there. The manual that I got is actually for the model O-12/U, and the U stands for UK, so I think they built a 220 volt model in the UK. But everything in the manual is easy to go by. I've built Heathkits many years ago when they were still being sold. The only thing the manual is lacking is it doesn't really get into the theory of operation. The theory of operation is essentially contained in a schematic, and I think it would have been nice if they explained it a little better, and I'm surprised that Heathkit didn't do that. But other than that, it looked like a really nice kit, and aside from giving you the joy of building it yourself, compared to the commercial oscilloscopes, the Tektronix or the HP scopes, it was significantly cheaper. I seem to remember that it cost about $60 or $65 to buy this, which was within the reach of many hobbyists. And I think, I couldn't find numbers, but I think that they sold quite a lot of these. I got this particular one locally. I've cleaned it up a bit. Didn't take a lot of cleaning. Somebody took care of it. And in our previous episode, I checked this for electrical shorts using the dim bulb tester, and it passed. And it is marked as consuming 80 watts of power. And when I read the current consumption, it was sitting at about 3/4 of an amp, and with 117 volts, that is close enough to 80 watts. That it was consuming. So the 80 watts is normal operating consumption, and does not include turn-on current and that sort of stuff. It's pretty bare bones. The screen isn't really calibrated, and it's a spherical tube. So if you don't look at this trace from exactly, if you don't have your eyes level with the center line, it'll look like the trace is curving up on the sides, and I'll show you that later, but that's the so-called parallax effect because of the spherical shape of the tube. And but that was a characteristic of the older tubes till Tektronix came out with their flat CRT technology that virtually eliminated the parallax effect. It is not calibrated. If you want to calibrate it, there's a calibration signal coming out of here that you, and when you display that, you can kind of calibrate with the vertical gain, make sense out of the scale, because you know you're getting a 1 volt signal. But it's even with that, I mean, you have to recalibrate it every time, and I wouldn't exactly call this a lab-grade instrument, but I think for the hobbyist, this was a great buy. Before turning it on and doing the checkout, I'm going to do, I guess, what you could call a pre-checkout maintenance on this. The outside's cleaned, the inside needs to be cleaned. The pots need to be lubricated and cleaned. The tubes, and especially the tube sockets and pins, need to be cleaned. And when you're dealing with an instrument like this, it's probably a good thing to do all of that maintenance before jumping in and doing the checkout, because simple existence of dirt in sockets and or pots can cause some weird problems that you may chase forever. So I do a few things like this before testing it. And let's have a brief look at the inside and then talk about the pre-checkout maintenance. Here's the instrument with its outer wear removed. I have cleaned up a bunch of dust on the inside. First thing you see is the tube, well, the CRT, which is completely unshielded. And that will cause some problems because tubes, the deflection circuits are very sensitive, and any source of magnetic fields will give you distortion on the screen. They also warn you in the manual that the scope may be affected by its own transformer down here, even though that's in a constant position as far as the tube is concerned, but it will still affect it. Now, what they tell you to do, that if you feel you're getting a lot of interference, you should reorient the scope until the interference minimizes. Now, yes, I did get some interference, and I played around with the scope, and I finally found some weird position where it worked, but what that means is you have to reorient the scope and then build your workbench around it. So that one could be a little bit of a hassle to get right. But moving right on, you can see it's got original caps in here, which eventually will need to be replaced, but I'm not going to jump the gun. I'm actually going to go and test some of them. It's also got these two cans with multiple capacitors inside. And looking at the back of it, you can see that this doesn't even have a proper neck board, but rather has a plug plugging into the CRT, which is directly fed from wires off of this PCB and the main PCB you saw before. And of course, here's the other side. Pretty much the same thing again. It's got a shield in here, and other than that, you know, the only thing that the original builder of this took a little bit too seriously is the manual keeps harping on keep your wires short. And I agree that that's a really good idea, but not this short. This is kind of, you got these wires right in the middle, being strung pretty tightly. I would recommend when building something like this, make the wires a little bit longer so you can properly route them and tie them off and make the interior look a bit neater. I mean, this was neatly built, but you know, these wires hanging in the middle are a little bit annoying. It's not that difficult to fix. You know, just put a new wire in and make it a little bit longer. But other than that, really no other complaints that I can think of about this. Now, the first thing, as part of the before checking it out, I'm going to do some maintenance on it so as not to try or go out chasing problems that are caused by something that can generally be avoided by doing some pre-maintenance on this. First thing we're going to do is look at the tubes, test the tubes, and before testing them, for those of you not familiar with tubes, the way to remove them is to grasp them. Now, let me add, practice thermal safety. If this thing was just on, make sure that you're not grabbing something that's sitting at a high temperature and burns your fingertips. But anyway, you grab it, you rock it in a circular motion while pulling up, and it comes right out. So what we'll do first is, using your favorite contact cleaner, lightly squirt these. Don't overdo it, just a little bit. Let the excess drip off into a paper towel, and then insert and remove this tube 2 or 3 times. And the reason we're doing this is, and use the same rocking motion to get it back, what this will do is it'll distribute the contact cleaner evenly between the pins and the socket contacts, and by doing it 2 or 3 times, it'll get rid of any sort of corrosion that may have built up in there that would cause some very strange problems. So let's have a look at the tube tester now. Here's my tube tester that was shown in a previous episode. I've done some more cleaning up on it. It still looks kind of ratty, but it is getting a little bit better. I mean, I tried window cleaner, I tried alcohol, I even tried some acetone on it, and but acetone is very dangerous because it'll attack plastic. I think that most of these are actually made of Bakelite, which should not be affected by the acetone, but there's things like the roll chart windows, the meter, and stuff like that. So acetone, you got to be very careful with it. What it did work well with was there was some paint. There was a lot of paint overspray here, and the acetone kind of took care of it, but I chickened out after a while because I didn't really want to damage anything. The one thing, though, I hadn't tried, and that works pretty well, but needs some elbow grease, is just a plain eraser. The eraser is really good on the textured areas, such as these, and you just got to stand there and apply elbow grease to it, and it just gets lighter and lighter and lighter. But I've done a little bit of it. It's going to take some more, and hopefully next time we look at this, it'll be really shiny. But anyway, so I tested some tubes, and I found something interesting about 4 tubes in. So remember, the way this works is you look up the parameters in the roll chart, which you can't see right now. So what I'm going to do is basically show it to you in the manual, and you can see over here, the tube I'm testing is a 12AU7. There's 2 entries for it, one for triode 1 and one for triode 2, and this basically tells you how to set all of the dials and what the minimum mutual conductance is to make this a good tube. So what I did was, there's 3 12AU7s in here, and here's one of them. Now, after my last video doing this, a viewer pointed out something really valuable to me, and he said, the very first thing you need to do with tubes before testing them is to do a short test on it, because otherwise you can damage the tester if there is a short in it. And the short test is very easy. You have this dial that goes from 1 to 5 and then to tube test, and if you turn it from to any position of 1 to 5, it checks pin shorts, and this will light up brightly, and you saw it flash maybe, and that is actually normal. It may flash when you're initially turning it, and that's not a problem, but if it comes on and stays on permanently, then you got a problem. So there's no short in the tube, and everything is set up as the entry in the table showed us. And now what we do is we put the push the test button over here, and we immediately get a deflection to, it's about 2,200. Well, it doesn't work if I'm obscuring it. Let's do it this way. So reading the top scale, it's about 2,200. The minimum required is 1,400. So this tube is good. Now, yeah, I'm pulling it out with the tester on, but that's okay. But then I found this tube over here, and I'm plugging it in with the tester on. And so, you know, you let the tubes warm up a little bit. You check them to see if they are getting warm, if the heater's working. I can't, you know, I can't really see it light up, but it did feel like the, yeah, it's getting warm. Not nearly as warm as the other one, but it's getting warm, so the heater's working. However, letting it sit in here for a while, and we wait a little bit, and then when we press the test button, absolutely nothing happens. The meter doesn't move at all. So that's a bad tube, and I won't even go in and check the second triode, because the first triode obviously is dead in here, and that tube needs to be replaced. I actually, previously to this, went and then tested all of the tubes, and pretty much everything in there was okay except this 12AU7. So I need to find a replacement for that and install it. But the tube tester just Saved me a lot of hassle. So this is probably a good time to look at the schematics, mainly because I'm kind of curious about what section the bad tube would have affected. But here's a schematic of the entire thing, and not a whole lot to it. We got the vertical section over here, the horizontal section, and the sweep generator, power supply, and the tube. And that's about it. Not a whole lot in here. There is a difference between the US and the UK model, and that is that the US model actually has a rectifier tube here, whereas the UK model is utilizing a diode over here. Another difference I found actually looking at the boards was this 100 ohm resistor, which is clearly shown in the schematics, is not on the board, but is actually shorted. So I didn't know whom to believe or what to believe, so what I did was I went through the actual step-by-step assembly instructions, and in those the 100 ohm resistor is not mentioned. So this was built utilizing obviously what was in the manual, so I guess the 100 watt resistor over here is not needed. Another thing to notice is that both the vertical input and the horizontal input are permanently AC coupled. You cannot ground the input or DC couple it, and that's going to most likely present some problems when you go to high frequencies, but other than that, it looks pretty standard to me. I'm not an expert on tubes, but most of this probably came out of the tube data books. But now to where the bad tube is. V5, and here's V5A and V5B are right here. And this tube was bad. And what this would cause is, this is basically the sweep generator. So you would be able to, what that means is you would probably get a trace, you'd be able to do a vertical and a horizontal trace, but you would not have been able to show a signal because it would never sweep the screen. That's what I thought. For fun, I can put the bad tube in and test that theory, but it's pretty obvious that if the sweep circuitry doesn't work, you're not going to be able to display any signals on here. So here you have it, and what we're going to do next is continue our pre-checkout tests. Now I'm going to measure some of the capacitance values. For the larger electrolytics, I'll use the ESR meter. But first, it's very important to discharge the capacitor because it will destroy this meter if there's any charge on the capacitor. Simply clip an alligator clip to the chassis. Everything's referenced to the chassis or grounded there. And then, in turn, touch all of the terminals of this capacitor. So now we know that that's discharged, and we can somewhat safely attach the ESR lead to it. So the top terminal is supposed to be a 50 microfarad at 450 volt cap. So our 50 ohms measures as 50 microfarads measures as 65, beginning to drift up, but it has a good ESR. Next we go to the one next to it, which is supposed to be 40 microfarads. And that one's also high, but the ESR is still good, and that's to be expected from these caps are original, they're 60 years old. We go to the bottom one, which is supposed to be 20. And that one says in-circuit leaky. That is most likely because of the way it's hooked up. To properly measure it, I would have to take it out of circuit Or what we can do next is measure the voltage on it, both AC and DC, and that's going to tell us more about that. But then to the last capacitor, which is supposed to be 20, and that one measures at 25, and the ESR is still good. So other than the terminal on the bottom, which we need to verify by doing voltage measurement on, even though the caps are high, I think they're still good enough for a functional test. Now over here we can see these real nasty, whatever they are, capacitors, encased. I mean, they're film capacitor or foil capacitors, but they're encased in wax or whatever. They're not paper capacitors. So, and since they haven't blown up yet, we should be okay. But those are too small for the ESR meter. So the way we're going to measure those is just with a multimeter. So let's remove this from the circuit and see if we can get the multimeter in the picture. And we'll go to capacitance. Hook up the ground to the chassis. And these are 0.1 microfarad rated at 1,600 volts. So obviously those are for the CRT. Let's get the glare out of here a little bit. And number 1 measures at 0.155. This is drifted upward by about 50%. And this one measures at 0.181, so this is also drifting up. Well, the good part is at least they're drifting up instead of shorting out. But yes, these are also high and will need to be replaced. But again, I feel that the value is good enough to do the functional test. I repeated that on all the other small value capacitors too, and most of them have started to drift up somewhere between 20 to 80%. But we're good there for now, of course. But we need to verify that one capacitor that kept saying leaky and see that if we turn this on and do a voltage measurement on it, what that's going to tell us. So we're still hooked up. So now what we need to do is plug this guy in, turn him on, and let him warm up for a minute. See, are we on? The tube's lighting up. Yes, they are. And I should probably have a look at the schematics to see what the voltage is supposed to be on that one. And the voltage on that one is supposed to be, I think this says it's a bit hard to read, but I think it says 400 volts. DC, of course. So let's measure the DC voltage on it first. And you can't see that. So let's put the meter over here and measure this. 429. So let me have another look at this. Oh, I guess that's not a 0. It's actually saying it's supposed to be 430. So we are right on here. Whoa. Look at this. I'm getting a different... No. The solder joint here is resistive. I just got a reading of... I thought I got a lower reading. But anyway, it's reading 430, which is exactly on. And let's see what the ripple is. So we can see the ripple seems kind of high because it's about 1%. well, no, it's a little more. It's about 1.5%, but 1.5% in an instrument like this isn't that bad. And I did experiment and measured some other things, and it turns out that what is causing the high ripple is, of course, that this is getting older. But the main cause of it is that's a 20 microfarad capacitor, and that value is just too small to lower the ripple. And to make sure that it wasn't bad, in fact, is I paralleled it with another 20 microfarad, and the ripple fell to 2.5. So the capacitor is actually, even though it's a little bit out of range with the value, the capacitor is still good. Now, there are a lot of high voltages in here, and I'm kind of curious about measuring those too, so let's do that. So what I'm going to do, or show on camera, is I measured some high voltages. They were a bit low, probably 5 to 8% low, but the schematics does say, and let me quote, voltage variation up to 20% normal. Now, what I'm assuming is it's talking about plus minus 10% from the listed value, and not 20% in either direction. So generally, we are within that. Now, to measure high voltages, you need, again, to be very careful. And another thing you need to use is something called a high voltage probe, which looks like this. Kind of looks like a miniature cattle prod. It plugs into your meter, and what this does in a nutshell is it divides the voltage you're reading by a factor of 1,000. So what that means is if you're measuring 1 kilovolt, the meter is going to read 1 volt. So let's put it in the voltage range, and the tops of these caps are supposed to be, and let me see, I can't tell the left from the right by looking at the schematics. But the one, so that the two red wires coming in are, I can't exactly tell which side is connected to what. But anyway, one side of it is supposed to be minus 1300 volts. So let's probe both sides and see what the meter says. This says minus 1,480 volts. And the other side says (1,360 volts), negative both of them. And glancing back at this, 1,340 is correct. That's what's coming directly out of the tube. Yes, of course. We can see the white and red wire coming and feeding this. Good thing it's insulated. 1,480, and the other side is one, should be reduced because this is dropping it. So the voltages, look within spec as specified, and I poked around the plug, the CRT plug, and some other places, and things still seem to look okay. I thought I'd give you a closer look at the high voltage probe. So here it is in its entire glory. It's a BK Precision PR28A, which is good for 28 kilovolts AC and 40 kilovolts DC. And it's very easy to use. You're well insulated because of the heavy insulation. It will also prevent arcing. And the tip of it is the positive probe, and the alligator clip the negative probe, which in this case you just clip to the chassis. And then you plug these two into a multimeter with a 10 mega ohm impedance, and you get your readings attenuated by a factor of 1,000. Very essential and useful instrument that you should definitely have if you're planning on working on CRTs or anything approaching or exceeding 1 kilovolt. As a final step, I moved around and spot checked a bunch of the resistors in there, did another visual check to see if anything looked cracked, broken, melted, or whatever, and everything seemed fine. The sample I measured the sample of resistors I measured all came back fine, even in circuit, all adhering to their tolerance levels, and there was no apparent damage on anything. So now let's do the prescribed checkout procedure as mentioned in the assembly manual. First it tells you what to set all the controls to, and basically then you turn it on and wait for a spot to appear. So let's sit here and wait for our spot to appear. And there it is. Let's get a little closer. So there's a spot. Let's move it away from the reticule so we can see it a little better. So it looks pretty round. I mean, there's you're basically supposed to adjust it using the focus, the intensity, and there's a spot-shaped pot inside the device. So if we turn the focus, we make it small. I cannot see that very well on the video, but it is getting sharper. And turning the spot shape does that. So the spot shape is pretty round. And then of course you play with the intensity until you have a round spot there. And then using the horizontal and vertical offsets to center the spot. And that's the very first test you do. Next we need to test the vertical amplifier and what they tell us to do. Did that spot just move up? It did a little bit, didn't it? Okay. So next, the way we do it is there is a calibration output of 1 volt sine wave that's derived from the AC input. So over here it's running at 60 Hertz. And the way to test the vertical amplifier is to turn up the vertical gain. And what that does, now the vertical input is set at the 100 multiplier, so let's bring that down, and we get a somewhat straight line. Does have a few bends in it, but remember that the tube seems to be extremely sensitive to external magnetic fields, and there's things all over my lab, and it would be kind of difficult to remove them, but this verifies that the vertical amplifier works. Now we're going to check the horizontal amplifier as well as the sweep generator, which looks like we fixed by, well, I hope we fixed by replacing the tube, but so if we look in here, let's see, what we need to do is set up a few things, but set the frequency selector to here, and there's our sine waves. Now I'm supposed to adjust this so we can see 4 cycles of the sine wave on screen, and the frequency fine adjust will essentially let me stabilize it. So there you go. We have 4 cycles of a sine wave as generated by the calibration output, and the camera actually reduces the flicker, but you can imagine at 60 Hertz it flickers pretty good. And of course we can go ahead and center this a little bit more. I mean, there's no reference point. you know, even though it is AC, and on any other scope you go to AC, it will automatically center itself on the horizontal line, but this has no ground reference as such. I mean, there's no way for me to set this. It is sitting in AC right now, but that has no relationship really to the horizontal position, other than me adjusting it and assuming that, oh, that's the horizontal position. Sorry, the vertical position I wanted to say. Well, this would kind of mean that the baseline's at 0 volts near ground, and these graduations here say plus minus 5, but that's, you know, not true, because the calibrator is generating a 1 volt wave, and so what we need to do is decrease the vertical gain if we want a true display. So something like this would be a true reflection of what is coming in. Now, on the video it looks a little bit like there's some cross-hatching in the trace, but that's an artifact. I think that's the way it manifests itself on video. The flicker manifests itself, because in real life I can see the flicker, but not that cross-hatching effect it has in there. So I think at this point it's telling us that, and that's pretty much the internal test. No, there is one more, and a last one, and we'll try that one. Next we feed the horizontal output, which is essentially the sweep, into the vertical input, and as expected it gives us a line at roughly 45-degree angle. And then we position it so it is centered about the origin. It's a little bit too high, but not exactly. And this adjustment is for getting rid of the little bend at the end of the trace over here. But thankfully this does have a trim pot for that. And we simply turn the trim pot until it's perfectly straight at the very end. That looks pretty close to perfectly straight. And that takes care of that. This is a good opportunity to demonstrate the parallax effect caused by the curvature of the CRT front. As we're looking at it from an angle above, it looks like the trace is curving up at its extreme ends and diverging from the baseline over here. However, if we move the camera down to be level with the center line, you can see that the curvature disappears, and it looks like it's exactly coinciding with the baseline now. And again, it's not even an optical illusion. Your eyes are seeing it correctly, but because you have a flat surface and a curved surface behind it, the distances between it, based on your angle of view, make it such that it seems as if that thing's curving up. So when you're using this, you better you better have eye level at this line here, otherwise your trace is going to look really funny. Time to wrap this up, and we'll do a simplistic bandwidth measurement. The manual claims that it'll go up to 5 megahertz, but I think that is greatly optimistic. And there's some other optimistic statements in here. For instance, it calls the CRT a 5-inch flat-faced screen. And I guess at that, maybe for that time this could be considered flat-faced, but it's nowhere near being flat-faced. So I very much doubt the 5 megahertz rating. But let's turn on Mr. Noisy here. And let's get started at 1 kilohertz. And the way I'm going to do the bandwidth check is, the reason I called it simplistic is that essentially I use a triangle wave and I keep increasing the frequency. And as this triangle starts turning into a sine wave, that's pretty much when you've reached the bandwidth of this guy. So let's adjust the display a bit. Nope, can't show it there. Do the fine frequency adjust, and that's a pretty good looking triangle wave on there. Now you may notice I put the case back on for whatever shielding that'll provide to the CRT. And this is kind of hard to see again on the video, but these traces are very sharp, but then as you get to this point they start blurring a little bit. And of course now it's sitting next to this guy, so that may have something to do with it. But so 100 kilohertz, yeah. So let's go up to, let's say, of course I went overboard, but let's go up to, I was going to go up to a meg. And so at a meg it still looks like a triangle, even though the peaks are getting rounded a bit there. Alright, so and we're getting that weird tail here. That was something that we adjusted for a straight line, but it's beginning to appear at higher frequencies at the beginning of the trace. So the next would be 2 megahertz. And you can still discern. Let's make it a little higher. And see if we can get it to trigger correctly. Well, almost. There you go. But it's getting pretty rounded, and for comparison's sake, let's go change this to a sine. There's the sine. There's the square. It doesn't look that different from the sine, quite frankly, so I would probably say that the useful upper range is 2 megahertz on this, or maybe 1.5. Let's see what it looks like at 1.5. Well, it looks still looks like a sine. So let's go down to 1. Yeah, I think it would pass at 1 megahertz, but anything above 1 megahertz is probably beyond its bandwidth. Yeah, you can see the difference between the sine, the square, and the triangle. So I would peg this at the 1 megahertz maximum bandwidth. So regrettably we reached the end. But here's a 60-year-old scope built as a kit. So I can't really call it museum quality, but you know, it was built from a kit and it's been thrown around for 60 years. There's some discoloration on this ring here and also on the inside, but generally it's in really good shape. It's a really light instrument. They used very light gauge steel to build the case and the chassis and everything. It's nice and stable because the transformer sits at the very bottom, so its center of gravity is right down there, and because the rest of the case is so light, it is very stable. How useful is this for day-to-day operation? Not useful at all, I would say, but I think it's a nice piece of history of test instruments and technology in general. So again, it's in cosmetically nice shape, and it does seem to work, even though the bandwidth, they claim 5 megahertz. That's I dispute that and say I would give it a 1 megahertz rating, but I don't know the exact criteria they used, and my bandwidth test is obviously very simplistic, and I'm using non-shielded wire, a non-BNC wire to connect it. Not that I can connect BNC to this, but so with things like that, you could probably squeeze out a few more kilohertz if everything was set up ideally, but here it is, and I would call it a boat anchor, but it's not because it's too light in weight. Well, I hope you had a good time. I would really appreciate a thumbs up, and if you haven't subscribed, go ahead and do so. See you at the next episode. I forgot to do this as you figure, so if you're still watching, enjoy. So the vertical is well, the vertical's running at 60 hertz, and so with 15 hertz we got a pretty stable display here, going up to half the vertical frequency. We get this going to 45, and then circle's not very round, but hey, I'll blame the caps on that. And you can just have hours and hours of fun with this. All right, I'll let you go now.